So let's look at how do we apply conservation of linear momentum in the case of a collision. Let's look at these two objects in a collision, a green one and a red one. They make an impact and they go their separate ways after that. Okay, so this is I means before the impact, initial, this during the impact, and here's F, final state, that's after the impact. Let's look at the force between them. Okay, the force between them. Before the collision, they don't see each other, they don't touch each other, the force is 0, so force is 0. Okay, at this moment, the collision takes place. Bang, there is a great force. So the force starts from here and it dramatically rises. Okay, and it can be pretty complicated, you know. God only knows what's going to happen. And then, before we know it, the collision ends and it goes back to 0. The force goes back to 0. So we're going back to the final case where the force again is 0. So, here's a picture of how the force changes. Look at this. This force can be a mess. First of all, the time duration, delta t, could be very short. We could talk about milliseconds or even less. And secondly, the force can be violent, very large, and difficult to trace because it can can be pretty complicated. You can imagine using Newton's second law to trace this force moment by moment. That could be a nightmare. It may not even be possible at all. For example, if these were two cars in a collision, you know the collision between two cars typically lasts less than 1 second, and who is there? Is it ever possible really to go back, to go back and trace everything, millisecond by millisecond like this? It's not possible, okay? But the thing is, usually we're not quite interested in what happened during the collision. What we want to know is what happens before and what happens after. For example, if there is an investigation on accidents, is it possible to figure out from what happened afterwards, say tire tracks or whatever, is it possible to trace it back to what happened before collision so we can determine whether this car was speeding or whatever, right? Is it possible to bypass the nasty part of the collision and figure out what happened before? Or sometimes, is it possible to start with the initial state and predict what happens afterwards? Okay, so you want to trace from final back to initial, or you can predict from initial to final. Usually we're not interested in the collision process itself. Just we want to find a link between initial and final. We want to find a bridge between initial and final. Where is that bridge? We want to bypass this middle point. Where is that bridge? Well, this is where the conservation of linear momentum really comes in to rescue us. Because after all, during such a brief moment of a collision, even if there were any external force, say consider the case of two cars, okay? Of course you say, oh, friction from the road, friction from the wind, but remember, it's an extremely short duration of time. Those forces are not all that large. Their impulse delivered over such a short time difference is negligible. Okay, what is the dominant force during the collision? That's the force between the two of them, right? Between this green guy and this red guy. Okay, between the two of them, that is the dominant force because that's the greatest force. It can manage to deliver a sizable impulse even though the time of act is so short because it's very, very large. But what is the good news? The good news is that if you consider both of these as part of the same system, okay, now that is the important thing. You don't separate them into different systems anymore. You consider them as part of the exact same system. Then the force between them, the force, okay, force between them, no matter how big it is, this is a pair of action and reaction, right? And they both have to be considered simultaneously, and guess what? They cancel out. And we know that for sure because, after all, that force F is between the green guy and the red guy, and both the green guy and red guy is part of my system, and therefore, by definition, this force F and that negative F, they're both internal forces. No wonder they cancel out, right? So what's that telling us? No matter how strong that force, how violent and how complicated that force is, we don't have to worry about it because they do not deliver any net impulse. Okay, only the external force can deliver a net impulse. These two forces cancel out. So there is no net external impulse delivered on the system, and therefore Here's before, here's the system after. There is something that remains unchanged from here to there. Something initial equals something final. And what is that? Of course, the linear momentum. Look at this. The external impulse is 0 because the force F is internal. It does not change the linear momentum. So P initial equals P final. That is how I link the initial state with the final state. Okay, I say initial momentum of the system equals the final momentum of the system. I don't have to worry about anything in between. That is the essence of applying the conservation of linear momentum to a process of collision. Okay, so we realize that when it comes to collision process, we have to exploit the conservation of linear momentum. Before we actually work on some examples, let's look at how we classify collision processes. There is something called elastic collision. There is something called inelastic collision, and within inelastic collision, there is a special case called complete inelastic collision or perfect inelastic collision. What are the differences? Well, we know that, we can't use conservation momentum, okay? So delta P equals 0. As long as there is no significant external force making an impulse, which is truly valid for most collision processes. We can use this, okay? We can always use this for most cases of collision. But what's different between elastic and inelastic collision? Well, in addition to the conservation of linear momentum, if the collision is elastic, then we also have conservation of mechanical energy. Of course, when it comes to mechanical energy, you have potential energy, you have kinetic energy, right? Gravitational potential energy has to do with position, but the collision, the brief process, we don't expect things to change their altitude, the height all that much. So basically, we say, if it's elastic collision, then we focus on the kinetic part of the energy. We say delta K equals 0, elastic. So not only is delta P equal to 0, but delta K is also equal to 0. So you do not lose any kinetic energy. Okay, an example would be, a basketball that's well pressurized. Okay, and you hit the floor with that basketball. It rebounds to almost the same height. Okay, ideally it rebounds to the exact same height. The reason why it rebounds to the exact same height is because you didn't really lose any kinetic energy upon collision. So the only thing that happened is that the direction of the motion of the ball has been reversed due to an impulse from the floor. Of course, that is a case where if you consider basketball alone, its momentum is not conserved because the floor gives an external impulse. But at least we can say the collision is elastic because the basketball did not lose any kinetic energy as a result. Only the direction of motion changes. So what is an inelastic collision? Well, in an inelastic collision, we can use conservation of momentum, but not conservation of kinetic energy. And that actually is very common, okay? Because in a typical collision, you're going to lose some kinetic energy. Say two cars, for example. Let's say two identical cars, one going this way, one going that way, okay? They hit each other. Before that, they move at exactly the same speed, let's say. So as a result of collision, they stop. Neither moves afterwards. Before the collision, each had kinetic energy. Afterwards, neither had kinetic energy. Obviously, all the kinetic energy are gone as a result of collision. So that is when delta K is not equal to 0. That's called inelastic collision. For majority of collision, that is the case. What about complete inelastic collision? Well, that is a special case where after the collision, everything got stuck together. So before the collision, everybody's moving every each way, right? Every which way. But after collision, everybody moves together with the same common velocity. They got stuck together. That is an example of a complete inelastic collision, which is particularly simple because there is only one common velocity at the end. I don't have to worry about, V1 initial, V1 final, V2 final, and so forth. Okay, so we're going to start our example with the case of complete inelastic collision because mathematically it is the simplest possibility. All right, so let's start our discussion with a one-dimensional complete or perfect inelastic collision. First of all, everything is one-dimensional right now, which means all these velocities, vector velocities, V1 initial, V2 initial, all these, can be can be reduced into just positive and negative quantities, okay? Because in one dimension, there are only two possible directions. You either go forward or backward. I can call one positive, the other negative. So I don't have to use the explicit version of vector. I simply use a plus sign to indicate this way and negative sign to indicate that way. All right, so let's see now. A one-dimensional, complete inelastic collision between a bullet and a block. Everything happens on smooth horizontal table, no friction here. This is before the collision, the initial state. And here's after the collision, final state. Let's see what happens as a result of the collision. The bullet of mass m1 comes in with v1 initial speed, at high speed, v1 initial. Okay. The block initially moves with a velocity of v2 initial. The mass is m2. Suppose the bullet moves faster, or maybe the block is moving head-on with the bullet. Anyhow, they have a collision. As a result, m1 and m2, the bullet plus the block, now move with the common final velocity, v final. Can I find v final? That's the thing. Can I find v final? Okay. Yes, you can, because there is a link between initial and final. What's the link? The momentum of the system, which consists of the bullet and the block, is left unchanged as a result of the collision. Why? Because during the impact, the only significant force is the force between the bullet and the block. That, in fact, is a friction force, right? Which slows down the bullet but speeds up the block. But that force is internal if I consider the bullet and the block as a single system. Therefore, it does not deliver an external impulse, therefore the momentum of the system does not change. Okay, but remember, you must include the block and the bullet into a single system. That is how you turn that force of impulse as internal force. So before the collision, P initial. What is that P initial equal to? Okay, so that would be M1, V1 initial. That's the momentum of the bullet, plus M2, V2 initial. That is the momentum of the block. After the collision, P final equals what? M1 plus M2 times the common final velocity V final, right? Because they have the same velocity. Okay, what can we say for P initial and P final? Well, they are equal. Right, because the momentum does not change as a result of the impact. I don't have to figure out, for example, how long it takes for this thing, for them to reach the common final velocity, how much is the force between the bullet and block that slows down the bullet and speeds up the block. I don't care. That's internal. Okay, so if you equate P initial and P final, you immediately can find V final. So I can solve for V final now. So V final equals to M1 V1 initial plus M2 V2 initial divided by M1 plus M2. It's just that simple. I know exactly what the, V final. I know exactly what the common final velocity is simply by using conservation of linear momentum. This is the simplest way to figure out the final speed. Okay, now I must caution you that in this particular case, you have conservation of linear momentum, but you do not have conservation of kinetic energy. As a matter of fact, the kinetic energy of the system is partially lost. You end up with less kinetic energy than you have to begin with as a result of the collision. Why is that? Because you have to understand, what does it take for kinetic energy to be conserved? Well, kinetic energy is only a form of energy. It's only one form of energy. There are other forms. We know energy as a whole, including all forms, must be conserved. But as a result of the collision, you see, the bullet comes in, right? It penetrates the block halfway. As a result, the bullet's going to slow down and the block is going to speed up. Why? Because there's a force between them. We know that's internal force. It does not change P. But after all, it's a friction, right? It is a friction. And so basically the bullet is rubbing against the block. It slows down. The bullet speeds up. That friction, due to the contact between the bullet and block, can partially turn mechanical energy into heat or sound. That's and or sound. Okay, so as a matter of fact, from the conservation of energy point of view, because other forms of energy are generated by rubbing each other like this, you're going to generate heat and sound, and therefore mechanical energy, which is in this case kinetic energy, must be partially lost. It must be less than it has to begin with. And as a matter of fact, I can show you explicitly that kinetic energy is indeed lost, partially lost, and I can show you how much it has lost. Okay, for simplicity, let's assume that before the collision, for mathematical simplicity, V2 initial is equal to 0. So the block is waiting for it. It's not moving at all. Okay, so I don't have that term. I don't have the second term. Okay, so let's see. I want to show you P initial equals P final, but K initial is not equal to K final. So assuming that V2 initial equals 0, so I have V final. So if V2 initial equals 0, just make it mathematically simpler. So V final equals to M1 V1 initial divided by M1 plus M2. Okay. Now, you know the final speed of both objects. Of course, you can find the final kinetic energy of the system, right? So the final kinetic energy equals to 1/2 times total mass M1 plus M2 times the final speed squared. This V final squared. Okay? Now, you plug in V final from here, and you just work out the algebra. That's 1/2 times M1 plus M2 V1 initial squared, and then M1 squared over M1 plus M2, right? I'm just doing the algebra here. Squared. Okay, let's rewrite it, okay? That's 1/2. There's an M1 squared. I'm going to take 1 out. I'm going to take that only one M1 here, and then I'm going to write down V1 initial squared. I'm going to factor this out. What's left? There's another M1. Okay, there's another M1. And there's M1 plus M2, but here's M1 plus M2 squared. Okay, so you have one term left, M1 plus M2. Isn't that true? Okay, you see, what is this anyway? 1/2 M1 V1 initial squared. Isn't that the initial kinetic energy that was carried by the bullet because the block was not even moving? This was the initial kinetic energy of the entire system. This is the final kinetic energy of the entire system. They're not equal, are they? Because of this extra factor here. As a matter of fact, let me move K initial to the other side. Then I have this ratio here. Okay, I have this ratio here. K final over K initial equals to this ratio right here, M1 over M1 plus M2. Clearly, this is not equal to 0. In fact, it is less. It is not equal to 1. In fact, it's less than 1, right? Because the denominator is greater than the numerator, so K final is less than K initial. That's exactly what we expected. It makes sense because part of the energy, the kinetic energy of the bullet was turned into heat and sound. Only part of it got transferred to the block. Another part was actually lost. That's why you end up with less amount of kinetic energy than you have to begin with. Now, let's look at this ratio here. M1 over M1 plus M2. What's M1? The mass of the bullet. M2 is the mass of the block. Let's imagine a situation where the block is extremely massive and the bullet is very, very light. Okay. You can imagine what happens in a case like that. You fire a tiny, tiny bullet into a huge, massive object. What happens to the object? It doesn't move, right? It doesn't care, right? It doesn't care. You're shooting a regular shotgun bullet into a Godzilla. He doesn't care, right? So, as a result, the final kinetic energy is 0 because Godzilla does not want to move. It doesn't care. So you see here, do I get 0? Yes, I do, because M1 is far less than M2. Okay, so the ratio is almost equal to 0. So that makes sense. So basically, in that case, you killed all the kinetic energy to begin with. On the other hand, if I'm looking at the other type of possibility, let's say you have a massive bullet hitting a styrofoam case, okay, which is far less massive. All right, so basically, or you can say we have King Kong charging on something very, very light. So as a result, what happens to King Kong? Nothing, keeps on moving. Okay, did he lose any kinetic energy? Not really. keeps on moving. So how much kinetic energy is lost? 0%, okay? 0% is lost. Is that true? Yes, it is. You see, m1 is far greater than m2 now, so the ratio is almost equal to 1. Not quite, it's a little bit less, but it's almost equal to 1. So you see, under these two circumstances, special cases, our formula does make sense. The interesting thing is what m1 equals m2. If that is the case, the ratio is 1/2. That means 50% of the initial kinetic energy is lost. That's a big loss, 50%. And yet, the initial and final linear momentum remains the same. Okay, so that is a case of one-dimensional complete inelastic collision. When we continue, we're going to continue with one-dimensional collision, but this time we're going to go to the other special case when you have what's called complete elastic collision. So you can combine conservation of linear momentum and conservation of kinetic energy in a one-dimensional collision. And we can see what happens then. And then we're going to move on to two-dimensional collisions to study the more general case.